Have you ever wondered how the music playing in the background of this video is processed by computers? I mean, of course, computer does not interpret it as we do in terms of notes and chords. All these sounds which are produced by human vocal cord are basically different kinds of waves, and computer understand them as mathematical equations that represent those waves. And since there are waves, there are sines and cosines. Music theory is not just a single application of trigonometry. It is used almost everywhere, from measuring the height of Mount Everest to how your favorite gaming character Mario tackles obstacles. Alright, enough of introduction. You must have been wondering what is going on in this animation in the background. If you were too indulged in listening to my alluring voice, just rewind and see how important conclusions can you draw just by merely looking at it. This animation has everything we'll be discussing in this video in a bit more detail though. This shows you how the graph of trigonometric functions are generated, why trigonometric functions are periodic functions, how the SOHCAHTOA works, which is basically a simple rule to remember the definition of trigonometric functions, and CAST rule, which tells us about signs of trigonometric ratios in different quadrants. Okay, let's move on and discuss these things in bit detail using another animation. Alright, so let's start. This thing right here in front of you is called a unit circle, and the reason is it has a radius of 1 unit. One thing I want to discuss before we go ahead is definition of another unit of angle, which is called radian, as you can see there. I'll tell you why we need to know another unit of angle if we already have degrees as a unit in some other video, but right now just take it as an important thing to know. Any angle in radians is basically the ratio of the arc of the circle, its subtends, and the radius of the circle. So in a unit circle, angle in radians is just same as the length of arc, because the radius is 1. You also see this pi here. The angles in radians are expressed as multiple of pi, just to make things easier for us. Now since we know that the circumference is 2 pi times radius of the circle, and in our case the radius is 1 unit, so it makes the complete angle, which is 360 degrees, equal to 2 pi radians, and hence making 1 radian equal to 180 divided by pi degrees. I just talked about this conversion because at first it is not easy to grasp the introduction of radians immediately, so you think of them in terms of degrees until you are comfortable. Having the knowledge of what radian is, let's just see where does these trigonometric ratios come from and what actually they are other than ratios. Let's just start with sine. Suppose you are standing right here at point A and you start moving on this circular path, and I am observing your motion from point O. If I see you in the direction of X, I'll see you coming towards me, and if I see you in the direction of Y, it will seem you are going away. Now suppose you stop at a particular point. How far you are along the y-axis from the reference point is sine of angle you are subtending, while how far you are from the reference point along x-axis is cosine of that angle. You can verify that in terms of definition of sine and cosine. Sine of angle theta in a right angle triangle is defined as ratio of side opposite to angle and hypotenuse of the triangle. In our case, the hypotenuse is 1 unit, so the side opposite to the angle is sine of the angle theta. Same way, you can prove that this length right here is cosine of angle theta. That man moving in a circular path analogy clearly illustrates why value of sines increases while that of cosine decreases when we increase the angle, and you can also see this right here if we change the angle. So we know how sine and cosine are positioned on unit circle, but what about other trigonometric functions? To find out where they lie on a unit circle, we have to think out of box. We know tan of angle theta is ratio of the side opposite to it and the side adjacent to it. So if we make somehow the length of side adjacent to angle theta equal to 1 unit, the side opposite to the angle will represent tan of theta. This hint is enough with one obvious thing that is clearly visible right here. This radius can act as our adjacent side, and constructing that opposite side perpendicular to our adjacent side is no big deal because we know that any line passing through this point will be perpendicular to our adjacent side, thereby giving us the required length. Can you represent all the trigonometric ratios on the unit circle same way? I'll give you a hint. They are Just try to figure out a way to prove that these lengths actually represent the trigonometric ratios which are indicated against them. That's it about this video. Before ending, I want to tell you why I took the unit circle approach, not the classic right angle triangle approach. There are countless benefits of introduction of trigonometric functions through unit circle. It is easy to understand the meaning of radian, and as we'll see in the next video, negative angles and trigonometric ratios of angles greater than 90 degrees also make sense only through this approach. Graph of unit circle, the cast rule, and periodicity of trigonometric functions, all these things are readily evident from unit circle. These things I'll discuss in next video, which will certainly be longer than this one. Until then, bye bye, take care and stay at home.